want to end up with is something like log n plus this. This term, it's not really clear how it behaves as n becomes large. So what I'm going to do is I'm going to do this. I'm going to say this term is equal to 1/2 excuse me. Let's do this manipulation a little higher. It'll become clear why I'm doing this in a second. I have 1/2 log n over pi k n minus k. This is equal to negative 1/2 log pi k n minus k divided by n, which is equal to minus 1/2 log pi k n minus k divided by n squared times n. So basically what I did was I multiplied here top and bottom by n, which is equal to minus 1/2 log n minus log pi k over n minus k over n. So substituting it all back in down here, this is equal to log n plus n h k over n minus 1/2 log n minus log pi k over n minus k over n plus 3. Why did I do that? Okay. What I wanted to know is what is so I know that the length is less than or equal to this. The average, the length of the code word is less than or equal to this. So basically, what do I have? L is the encoding length of an n-bit sequence. So we start with a source whose probability is pretty close to k over n. So this should be something greater than n h k over n. But I want to know what's the penalty beyond h k over n. So on the right, we have n h k over n, and then the penalty is taken up in all of the other terms. So let me write this a little higher. So what we have is n h k over n less than or equal to L, less than or equal to, let me write this term first, n h k over n, plus I can collect this term and that term, plus 1/2 log m minus log pi k over n minus k over n plus 3. So this is the entropy, the assumed entropy of the source right here. And these are penalty terms. So this is the amount that I'm paying to encode this universally. What I want to know is, all I want to know here is the asymptotics. In other words, as n goes to infinity, which of these terms dominate? If I look here, k is always less than n. That means n minus k is always less than n. Remember, k is the number of ones in the sequence. So that means as n goes to infinity, this is basically order 1. As n goes to infinity, this is basically order 1. So basically k is k should be thought of as proportional to n. So the number of ones in the sequence is some fraction of n. So as n goes to infinity, this is order 1, this is order 1, so this is log of something, order 1, so that's also order 1, plus a constant. So basically what we end up with is that this is nhk over n, plus 1/2 log n, plus order 1, plus terms that don't increase, or that approach constants as n goes to infinity. So in other words, the total cost of encoding is log n. So per source letter, if I divide throughout by n, I have h and k over n less than or equal to L over n less than or equal to h k over n plus 1 over 2n log n. And as n goes to infinity, what is this term? What's log n over n as n goes to infinity? 0. So in other words, asymptotically, as n goes to infinity, I don't pay any penalty. So my scheme, admittedly impractical, of counting the number of ones, creating a source code for each possible number of ones, enumerating all the possibilities, this is a very good scheme. Now, we agree, therefore, that universal coding of binary sources is possible at rates close to entropy of the source. Now, the question is how to do it. So this scheme is not practical. We can't specify basically n possible codes, each of length n choose k. The complexity increases factorially in n, so that's not really an option. What would be nice is if we could translate it back to one of the coding schemes that we've already talked about. So in order to come back to one of the coding schemes that we've already talked about, Shannon-Fano-Lass codes and Huffman codes, what we really need is we need a probability distribution. So if you like, those schemes take as input a probability distribution and produce a code. So what we would really like is, given a source sequence, even if we don't know the underlying source distribution, what would be nice is if we could somehow produce a universal distribution that leads to a nice code using one of those techniques that we already know about. So what we're going to do is we're going to form a universal source distribution using a mixture over all possible source distributions. In other words, I don't know what the input source distribution is, so what I'm going to do is I'm going to forget about actually knowing it accurately and just, by mixture, what I actually mean is I'm going to assign all of the possible source distributions a probability and basically take the average over all of those possibilities. So what do I mean by that? Let's let theta equal the probability that x equals 1. So remember, this is an IID source with n letters, and the only thing I don't know here is probability x equals 1, which I'm going to call theta.